Okay, so during my PhD, I spent about half my time watching videos of baby starfish swimming. And the reason I think that that's something worth doing is because we're really interested in this system for what we can use it for to learn about the sort of evolutionary constraints of a lot of early animals. Because baby starfish, like a lot of invertebrates, share a lot of common features in the physiology, and we're very interested in seeing whether there's some sort of physical constraints that tell us something about why these features are shared by a lot of invertebrates and thus the early animals. The main thing that we're interested in with the starfish is that baby starfish undergo metamorphosis. So many of us are familiar with starfish as these sort of sessile things that live at the bottom of the ocean. They don't really move that much once they've settled. But early on in their life cycle, starfish actually, they look like little spaceships. They have bilateral symmetry, they're these gossamer objects, and importantly for our purposes, they're freely swimming for about 2 months of their lifespan. And during that time, they sort of wander around the open ocean, they find these jet streams, and they're able to move very far. And they're essentially just feeding the entire time. They're hunting phytoplankton blooms, during which they can gather as much food as they can before they eventually metamorphose. So this idea of a two-phase life cycle, a biphasic life cycle, is something that pops up in a lot of invertebrates. And so we're interested in the sort of functional constraints that could lead to it emerging. So this is a video of some 2-week-old starfish larvae. And the one thing that I really like to emphasize in a video like this is that these are low Reynolds number swimmers. They're millimeter long. They swim about half a body length a second. But despite being at low Reynolds number, you see a lot of individual variation in the swimming strategy. So you can see in this video, the animals, they do barrel rolls as they swim sometimes. Sometimes they do these loop-de-loops. At one point in the video, you can actually see 2 starfish come up to each other. They touch, and then they do this very nice 3-point turn to change direction. And so there's a lot of complexity in the way they swim. And it's because this is a low Reynolds number swimmer that's coupled to a nervous system, which gives it a whole set of degrees of freedom that otherwise you don't normally observe at this length scale. And as an example of the sorts of complexity we see in this system, if you take a single one of these animals and you image the flow fields that it generates around its body, you see that they're way more complex than we typically associate with flows of this length scale. Most of us are familiar with low Reynolds number swimmers that generate 2 vortices and they're fore, aft, a pusher, or polar. But these starfish larvae are producing up to 12 vortices around their bodies at a given time. And these vortices are dynamic. During this video, you can see the vortices coalesce, they decoalesce, they'll change shape and size. Meaning there's a lot of complexity being encoded in the local flow field by the starfish larvae. And because this is a very low Reynolds number, these features, these vortices, are actively dissipating power, meaning that the animal has to continuously dump energy into the fluid in order to generate these features. So to us, that suggests that this is some sort of adaptation, because otherwise it wouldn't be energetically reasonable to do something like this. So the actual cause of these vortices is actually pretty simple when you zoom in on the larvae and get an idea of what's going on, which is that like a lot of other swimmers at low Reynolds number, starfish larvae are covered in cilia. But unlike something like a paramecium or something, a starfish larvae has up to 1 million cilia on its body at a given time because it's 1 millimeter long, so it's a lot of space. And these cilia are primarily concentrated in ciliary bands, which are these linear arrays of cilia that outline the periphery of the animal. And the nice thing about these bands is that's where the nervous system of the starfish lies, so control and the actuation are sort of coupled along this one-dimensional array. And so if you zoom in on the ciliary band, you can imagine if the animal just wanted to swim, then when it actuates its ciliary band, it would have a very uniform streaming flow past its surface. Particles would just move along the boundary, and so you would have propulsion. And so when we see these vortices form in the system, it's because portions of the ciliary band have cilia that are beating in reverse relative to the prevailing current. Whenever you have this reversal region, that's where streamlines lift off the surface, and that's where you see these eddies forming around the system. So the actual function of these eddies then is very simple, because if you'll notice, particles get entrained within these eddies. And so if you watch these videos for a really long time, you'll actually see that the starfish eats the particles out of the flow. And what's happening is that these particles circulate in the region in the near field, and when they actually get close enough to the cilia to get intercepted, to touch the cilia will actually lock down on them and pull them out of the flow. So there's sort of 2 phases to the feeding mechanism, a hydrodynamic entrainment, and then actual interception when particles get close enough to actually contact the surface. So we can take this sort of simple ideas, the idea of a near field and the idea of this local interception process, and we can use it to construct a minimal model that reconstructs the essential features of this flow field. And in order to do that, we're going to sort of ignore the morphology of the larvae for a second, and we're just going to map the boundary conditions to a circle. And we can use stuff like curvature weighting to account for morphology to leading order. And when we do that, we can actually do pretty well reconstructing the shape of the flow fields. We get some artifacts, but it generally works pretty well. And the nice thing about doing that is that there's actually a known analytic solution to Stokes' flow in this regime for a circular object exerting a slip boundary condition. And the solution has this very nice hierarchical structure that gives us some sort of insight on what's going on in the system. So the leading order mode in the squirrel model, as people call it, the leading order mode is a system scale mode. So that corresponds to this case I described where you have a streaming flow past your surface. And so the first order mode, the B1 Fourier coefficient, corresponds to the swimming speed of the system. And then you have this infinite series of higher order coefficients, and those would correspond to higher level degrees of actuation along the surface, or more and more reversal regions. And because each of those has a characteristic decay length scale, the idea in this system is that as you have finer scale actuation on the boundary, you get smaller but more powerful vortices in the near field. So there's this local hierarchy in the flow field that emerges from this model. And the nice thing about having a model like that is we can use it to interrogate why these vortices would create a local increase in the feeding rate. And what we see is that if you add more reversal regions to the surface, or you activate higher order terms in this model and get more and more reversal regions, as you generate more vortices around the body, more particles tend to get pulled into the near field. And this is essentially a geometric effect. It's a focusing effect where particles get pulled in. But the thing about doing that is when you're creating reversal regions, you're naturally allocating cilia away from creating this first order Fourier mode that causes a streaming flow past the surface. And so you always create a decrease in your swimming speed when you create more vortices. So it's just that there's this hydrodynamic trade-off between the feeding rate and the swimming speed that represents a sort of functional or evolutionary constraint that emerges from understanding the hydrodynamics of a system like this. But as you can imagine, the nice thing about working with animals, things with nervous systems, is that the actual dynamics of what's happening is often far more complex than this. So this is an animal that's actually adaptive, that is actually changing its boundary conditions as we're sitting watching it, and as a result, it's changing the flow field around it. It's a starfish that can't make up its mind regarding what swimming strategy it wants to implement. So during this video, the animal actually shows as many as 4 to 8 to 6 vortices at different times. So just that there's some continuous modulation of the gait in this system as the animal adapts its boundary conditions. So generally that struck us as sort of a hard problem because behavioral variation is coupling the fluid dynamics to a lot of sort of processes that we can't necessarily view. But what's incredible about this specific system is if you watch it over really long time scales of, say, around 15 minutes or so, you actually notice that there's a natural periodicity in the time scale of the fluctuations in the current. In other words, there's unsteadiness in the flow, but it's periodic unsteadiness. And so what we can do is we can take these long videos and we can use the fact that we know the fluid mechanics at short time scales very well to quantitatively deconstruct the behavior by first extracting the boundary conditions, that's the slip boundary condition, and a low Reynolds number that's equivalent to knowing the full flow field. We can then map that across time to get a chymograph which shows the boundary conditions as a function of time, and that should be a summary of what the behavior looks like at different time points. We can then take those boundary conditions and we can fit those to the squirrel model and extract what the values of these leading order Fourier coefficients are as a function of time. And what's cool about doing that is basically there's all this complexity in the flow field, there's all this variation that's hard to sort of understand when you look at it, but when you actually project it onto the space of this model, the actual underlying dynamics is low dimensional. It's just a few Fourier coefficients that we need to keep track of as a function of time. And on top of that, even if you don't believe that the model is complete or if there's details in the model that we shouldn't be accounting for, you don't even have to do that to see this low dimensionality. You can just take the bare PIV and just run PCA on it and pull out the leading order eigenmodes, and you'll still see this sort of multi-scale analysis where you have two competing modes that have different timescales associated with them. So there's sort of two independent ways to see this blinking behavior in the flow field. And the nice thing about having an analysis technique like this is that we can then use it to analyze the effect of perturbations in the system. So here the animal on the right, we've soaked it for about half an hour in magnesium chloride. And what magnesium does in this system is it's a global inhibitor of the larval nervous system. Essentially what it does is it doesn't mess with single cilia, like the boundary conditions persist and the cilia still beat to form the flow field, but the central nervous system loses the ability to tell the cilia to change the beating direction. And so as you can see in the wild type, there's all this sort of unsteadiness and irregularities and the streamlines of particles, but the animal that's treated with the drug, it becomes completely uniform due to the effect of the drug on turning off these behavioral variations. So in other words, we can use this perturbation in this quantitative analysis to see the effect of perturbations on the behavior in the system. And what we like about this particular technique is that when we turn off the blinking or we turn off these behavioral variations, we actually observe a huge decrease in the local feeding rate. And it's not just a decrease in the number of particles that get eaten. If we actually use particle tracking to quantify how many particles had the opportunity to be intercepted, we find that there's a global decrease in the number of particles that access the near field of the larvae when there's no behavioral variation and no blinking. That suggests to us that there's some hydrodynamic role of this blinking phenomenon in the system. We can then return to our model and use the model to understand what's happening and how blinking would be increasing the feeding rate by basically building this time variation into the squirrel model by having these time varying coefficients. And when you do that, there's essentially two timescales that matter. There's the timescale between blinks and there's the duration of blinks. We can just do a naive search of the full parameter space. And when we do that, we find that there's an optimum and intermediate timescales that correlate with the timescales that we see in our experimental data, suggesting that there's some fine-tuning of the behavioral variation towards this hydrodynamic optimum. So I won't linger on this just for time reasons, but we have some idea of why this timescale is optimal. And if you look at the Lyapunov exponent in the experiments or the transport measurements in the theory, you can actually show that there's a cascade at this specific timescale, suggesting that there's some weak chaotic mixing system happening at this timescale. But I'll talk more about that another time. So for there, I'll go ahead and wrap up. And for the remaining time, I'll take any questions. Thank you.
Questions? Go ahead.
How does the organism actually control the blinking rate?
How does it what?
How does the organism control the blinking rate?
Yeah, so people who have looked at, we haven't done like a nervous system patch clamping, but people have looked at blinking before in other invertebrates. It's sort of a phenomenon that pops up in a lot of systems. It looks like it's a central signal that affects, that's sort of sent to all the cilia at once, and that's part of why we can inhibit it so well, is because it looks like if you do something that affects the entire nervous system, it'll affect just the blinking timescales. But at the same time, there doesn't seem to be feedback on like obvious perturbations like local fluid density on the blinking rate, suggesting that's more like a rhythm than something that's actively being modulated.
How does it depend on the viscosity of the fluid in which, because I think in the ocean there can be quite a bit of gradient and
Right.
viscosity, so does the changing the salinity and changing the and affecting the viscosity, should that have an effect?
So I mean, at least as far as the analysis that we've been doing is we're assuming essentially Reynolds number equals 0, so that the viscosity won't pop up as a term in our model. Practically, we've tried stuff like adding dextran to the water to make it feel thicker to the animal, but that tends to just cause the animal to die because it has trouble breathing at that point. So it's not clear to us. There could be some inertial effects like streamline crossing, especially when these particles do these sharp turns at blinks, but we haven't really quantified that yet in our data. Yeah.
Okay, there are lots of questions. The session is over, but you can go ahead and ask. So if anyone needs to leave, you can go because it's...
So how did you choose the B coefficient? Is there any physical explanation apart from the B1?
So basically, because you can imagine you could pick another orthogonal basis functions that's more aware of morphology. But essentially, the B coefficients are just the Fourier-Mez on the surface, so they tend to correlate with length scales over which the reversals happen. So you might not have like a perfect sine wave on the actual real swimmer, but you do have characteristic length scales of reversal, and those correspond to which B will be the largest at that time.
Did you try solving the field for the actual shape of the larva with the conformal mapping? You can map the circle to the, you can get an exact solution.
Yeah, so there's these numerical libraries that use this like Schwarz-Christoffel transform to map stream functions over. We definitely looked at doing that, right, with some polygonal approximation of the animal. I mean, the short answer is we couldn't get really consistent effects just because when you run those libraries, you find that like these small variations in how you do your meshing affects sort of the structure of the streamlines a lot. But
that's probably a feature. That's probably what actually happens.
Yeah, I mean, so I think that when you have really sharp concavity changes on the surface, you might get stuff like cornerettes and stuff like that. But like at the same time, when we do something like a fitting to the model, we can make sure that we're sort of accounting to leading order for small fluctuations in curvature. That's in Blake's original paper. So yeah, there could be like finer geometric features, but a lot of this stuff like this vortex trapping region was sort of independent of whether the specific morphology is there.
I have a question about, have you looked at all how things change as it grows in size?
Yeah, it seems to get more complex. At some point, we're careful about working with it because at some point the muscles come online, so the animal's actually changing shape as we're imaging it. And so then the flow fields get quite complex because then you have sort of these extra short time scale actuations. I'd say that there's generally more reversal regions, which might suggest that the nervous system has some length scale associated with actuation, and that you're just getting more tilings of that pattern. But we haven't looked at that more explicitly than that.
Okay, let's thank the speaker and all the speakers of the session.